nitrogen work. We've actually built a pilot facility of this up at Vanderhoek Dairy in Linden, Washington. And we also were down in Jerome, Idaho, working with another dairy down there, piloting another idea that we had this last week. Okay. I want to talk a little bit about biofuel crops. We have done quite a bit of work in biofuel crops. And I'll say this, the reason that we do a lot of the work that we do is because we can get it funded. And everybody's crazy about bioenergy, and the feds are throwing money at it, so we can get a lot of money and do this work. And so we've done quite a bit of work. Some of the more interesting ones, flax and sunflowers, hybrid poplars, that stuff's been going on for a long time. We've also been doing some work with a couple of the C4 grasses, switchgrass, which I'm sure everybody's heard of by now, and Arundo donax, which is a noxious weed. Quite a few of the potentially good biofuel crops are noxious weeds. And we'll go further. One of the things that we're really interested in terms of the biofuel crops is alternative crops that help some of our conservation-based rotations work. And so, you know, if you go no-till wheat on wheat on wheat, you may have some issues. Having an alternative crop you can bring in. Same thing with potatoes or other crops that we use in the Columbia Basin or under irrigation. These crops, if the markets come there, could potentially play a role that helps some of these conservation-based systems work. Plus, there's this other side of it. Some of these crops have some really cool properties that we can extract as substitutes for some of the things that we use. So I'm sure that you've heard some about canolas and mustards and brassicas and some of the interesting things they do when you use them in rotation with wheat. Well, we've been doing quite a bit of work. Some of this happens at University of Idaho, but we've been doing some other work at WSU in terms of looking at some of these brassica seed meals for their characteristics as both fertilizers and pesticides. And one of the issues is there's both a biological thing that's going on and a chemical thing that's going on. Sometimes they work together and sometimes they work against you. And we don't really know yet exactly what's going on. So we've been trying to figure that out to understand the mechanism so we can make it predictable. But basically what we've got is a situation where you apply this material, there's a lot of nitrogen immediately available, which is good for plants, but then the flip side is the stuff kills everything you plant into. So that's not going to work. But what we're trying to do is figure out what the sequencing is or what types of mix of materials we can use to create a product that when you apply it, you get the plant, you know, essentially it's Roundup followed by a nitrogen fertilizer when you're ready to plant. So we've done quite a bit of work on that and have some good ideas. Okay, the next thing I want to come to on this issue of biofuels and energy and substitution is one of the concerns that we've had, and that is keep coming back to nutrients. And if we start taking all of these materials and growing them and exporting them to produce ethanol, we're changing our nutrient balance in the state, and we're also changing our carbon balance in the state. So back to the Cook farm, looking at wheat residues. And I know a lot of the stubble here is either baled off and removed or burned off historically, but there's value in the residues. And that's why I told Craig, you can't just call those residues waste, because there's carbon value to them, there's nutrient value to them. We've done some analysis on the Cook farm using all the database that we've got. That basically, we can do a pretty decent job producing ethanol. Not quite 150 gallons per acre in Pullman. That's okay. It's not great, but it's not bad. Certainly in certain places on the field, so basically the valleys, you do a lot better just because there's so much more residue. But what we also did is we entered in the harvest efficiency for those residues and said, what if we took all that residue to the factory to make ethanol? What have we done to our carbon and nutrient balances? And you can see there's only one little spot in the field that we felt we produced enough residue that if we took it, we'd still have enough just to maintain our soil carbon levels, which is a pretty important part of fertility. And then we looked at the nutrient side of this. And so we kind of went through the field and said, you know, NPK and S. If we took those residues and shipped them off, what are we shipping off in terms of value that we have to then substitute back in? And these numbers are actually 2 years old now, and they've adjusted. But we discovered, you know, it's at least $13 a ton of residue that you're basically taking off your fields. So where we came down to is, you know, it doesn't necessarily mean don't do it, but it does mean if you're doing it, get paid for it. You know, don't just give it to the Department of Energy who said they were going to take it from you for nothing. We also, you know, I talked about the switchgrass, the Arundodonax, the huge grasses that we can grow where we irrigate. We move a lot of nutrients off when we export those materials too, and it's all going to go to the central factory. So what are we going to move off? Basically, you know, if we take the residues from corn or wheat out of irrigated production, this is kind of the amounts that we're taking off per acre. And then switchgrass. We're also we're actually exporting more nutrients when we move switchgrass off than we would if we take all the corn stover and wheat straw. So we've got to have a way that if we're going to move these materials for energy production, to recover some of that nutrient and get it back on the field. Otherwise, you know, we're robbing Peter to pay Paul. We may have more energy security around our fuels at the same time we're giving up our energy security around nutrients. And if you don't know, where do we get our nitrogen from? Middle East and Central Asia. So, you know, we can't just make that trade-off without thinking critically about it. One of the types of products that we're looking at, and we have mixed opinions on the potential here, but everybody seems to be really excited about it, is biochar. So one of the processes by which you can recover fuel, ethanol, or anything like that from grasses and other biomass, or even my shirt, is what's called a thermochemical platform. So instead of bugs eating the material and making ethanol, we actually are essentially high heat pressure burning the material. Biochar, by any other name, is charcoal. However, there are some real interesting characteristics about the temperature and the pressures that it's cooked at, and the quality of the fuels that can be derived, and the quality of the char. And so we've looked a lot at this char. Department of Ecology, again, wanted to fund this project because they're looking at ways they can manage that waste. In fact, I should say the Department of Ecology funded the biomass inventory as well, because they're the ones charged with waste management, and they're looking for ways that we can have more beneficial uses of these wastes. So three cheers for the Department of Ecology tonight. But this material isn't real nutrient dense, but it is a recalcitrant form of carbon that, you know, we can recover energy and send back this material. We're also thinking, I talked about the brassica seed meal earlier, which is a high nitrogen material. Commingling these materials may actually provide the right benefit we're wanting in terms of exporting carbon and nutrients back to the farm after we've taken them off for energy. So we're looking at this one. It's kind of expensive for a soil amendment, and I'll just stop there. We just finished a report that'll get posted very quickly if you're really interested. But this is a little bit more on that. Basically, the temperature that's optimal for char production, and this is an issue, is not the temperature that's optimal for fuel production. So if we want to produce the most char, we want to be here, but if we want to produce the most energy, we want to be up here. So this is going to be a trade-off. You never get anything for free with energy. And if we want that material to go back to help with some of the stable carbon and nutrients that we depend on in our systems, we're going to take a trade-off and produce less energy. Okay, so the last thing I've got tonight is this idea of redesign. And the theory here is we've done things in our agricultural systems because we've had petroleum-based materials. They've enabled us to do some amazing things, and don't ever let anybody tell you differently. Our yields are tremendously high compared